Hello and welcome to the eLab Innovation Podcast, the podcast on e-mobility for research and industry. My name is Simon Voss and I'm the Managing Director of eLab of RWTH Aachen. Coming up, we are releasing a couple of special episodes on the topic of non-road mobile machineries. In short, NRMM. Herein, we present keynotes as well as discussions with several experts from the field. Today's episode is featuring a keynote that I held at the 6th Annual Forum for Non-Road Mobile Machinery. Herein, I provide an overview on the sector of NRMM in terms of global emissions, in terms of CO2, NOx, but also particle emission, and what the technical challenges, but also the big potential in terms of electrification is in order to make this sector of mobile machinery more sustainable. So stay tuned and looking forward to the episode. Looking at on the right hand side, this is an interesting material which is lithium iron phosphate, which was believed to be dead about 4 years ago. Everyone was thinking, okay, this was an old technology, it doesn't have any use. And then suddenly, on the Asian market, there was some innovation happening, and now everyone is talking about LFP again. Welcome everyone, also from my side, to the second day of the conference. Today I want to talk a little bit about examining the innovative trends of R&D in terms of NRMM and what we can bring to the table with eLab. To give you a quick introduction about myself and our institution, so my name is Simon Voss, I'm the Managing Director of eLab of RWTH Aachen, which is not too far from here, about 1 hour drive. And to give you a bird's eye perspective, so this is our research campus, and eLab is basically an institution where multiple institutes come together and share their core competencies on the practical research on the electric drivetrain, which includes motor, power electronics, as well as, very important, the battery. And to some extent, which is more and more coming, fuel cell components. That said, I would like to give you the outline of today's presentation. We start off with the status quo of the NRMM field from our perspective. Then we go over to an overview of the R&D trends that are currently happening. And lastly, I would like to give a couple of examples what we could offer and bring to the table for further development. So my apologies if I go a little bit quickly over the first slides, because I think you may all know the general storyline that we need to save CO2, etc. But nevertheless, I think it's still important on understanding how we can meet the fossil fuel targets, and then I will go on to a couple of more points from a technical, economic, and organizational perspective. What the status quo holds. So let's jump into it. Considering CO2, we need to save CO2, of course, but is that really important for the R&M sector? Looking at it globally, yes, it is important, of course, but as you can see on the right-hand side, I think particulate emissions as well as NOx emissions are even more important, looking at from the bigger scale. And especially the agricultural sector as well as the construction sector play a critical role there. We have 20% of global CO2 emissions in the construction field, as well as about 29 or 25% here in the agricultural field. I know about 1% of each make up the total CO2 emissions that go into the R&M sector. As I said, the particulate emissions are very important, and up here on the right-hand side, you see the emissions during a working day. Generally, the thresholds, as you can see on the left-hand side here, are about 3 to 4 micrograms per cubic meter on the construction side. And what you can see here is that over a working day in an inner-city environment, the particulate emissions can increase quite significantly and exceeding the allowed thresholds by many times. This is important for Europe, but this is especially important in the Asian region, where the standards are currently a little bit lower. So therefore, we really need to electrify the drivetrain of construction equipment, but also of agricultural equipment, because the diesel engines there even have higher particulate emission than if you look at the construction machineries that are in place right now. So that said, as I said, I will go a little bit more quickly over the first slides, and then we will focus a little bit more. So what does the market hold, and what do we need to focus on? We see that generally the trend in NRMM is positive, so the market is emerging. Here you see a graphic for the construction machinery. We are around 230 billion euros in the year 2030, to just give a rough estimation of what the market size will hold. Currently, Germany makes up about 9 billion for the agricultural sector and about 13 billion for the construction sector. So generally there is a trend, although the NRMM sector is still in its complete turnover relatively small with 3%. So looking at the challenges that we are facing, status quo. First of all, we look at the technical challenges, and those are especially for the energy supply. We need batteries or fuel cells in order to power our machines, and the current performance, of course there's a wide variety of different chemistries that can be applied, and we'll come to that in a minute, but that is still a limiting factor, which is kind of holding back all the innovation in the sector that could be realized right now. And looking at our NRMMs as a whole, the functional safety has to be considered during the development. And what is also very important, I think, are the 2 points on the right-hand side. The robustness of the machinery that is put into place is critical. Looking at an EV in comparison, right? We have quite a simple business model. We have to get people from point A to point B. But the requirements in the NRMM sector are very diverse, and which are also very high in its technical challenges, meaning there's a huge variance and an important or a high emphasis on specific tasks that have to be fulfilled. Looking at agricultural equipment like harvesters, very particular requirements, which, and there come to the fourth point here on that slide, state additional challenges looking at it for the complete product. Meaning we have the energy density and the provided energy from the battery, and then we have a high energy demand in terms of the applicational field. I mentioned the harvesting as an example. And then we have the technical challenge that the infrastructure, meaning the technical infrastructure for charging, is for those applications also very often the times not given. Status quo, right? We are working on improving this, of course, but I think, especially for the agricultural sector, it will still not be in place in the future. So it's not an infrastructure solution that we have to come up with, but a rather technical one on increasing the capacity and the energy utilization, the efficiency of the electric drivetrains for those applications. Coming to the next point, looking at it from an economic perspective. I think everyone knows that battery prices are dropping, are decreasing, and that's a good sign actually. However, they are still too expensive for many applications if we consider high energy intense applications such as tractors, such as harvesters, etc. And here's just a little example out of a paper that looks at a fuel consumption of 10 liters per hour. Right? So that's this line here, and what it would equate to for an 8-hour usage time in battery cost given 200 euros per kilowatt hour as a baseline price, which would result already in 50,000 euros just for the battery. So in this example case, it makes up 40% of the overall vehicle, which is not, maybe not too high for some applications, but generally at a threshold where you would still consider a hybrid or more traditional drivetrain. However, in order to decrease the cost, and we will come to the point of large scale or using the scale effects to further increase the economic burden, there are solutions in place, or actually in the development, on modularizing the the given battery packs in order to decrease costs. But I will come to that in a minute. So only key message here is it's still a burden implementing the battery drivetrain. If we increase the fuel consumption per hour, battery prices are decreasing, and there will be a touching point at some point where it will become more feasible. But I think we still have to wait a little and also take other challenges into consideration, and that is what I would coin here as the operational point of view. So as I mentioned with the agricultural sector, charging infrastructure is not everywhere available. And the question now is, how can we solve that issue? The one would be just increasing the capacity. We just saw that from an economic point of view that may not be suitable. And then there are like solutions like inductive charging, overhead lines, like using a pantograph. Those may be solutions, but I think only in particular areas where it really makes sense. And one thing that is also important is the charging time. And this is what I would like to emphasize in a minute. Before that, I would like to emphasize two more solutions that may be there. Battery swapping is, I think, something that many companies also used in the past. For small applications, we see a decrease in battery swapping technologies because lithium-ion technology is ready to power this through the working day. But for high energy intense applications that are rather stationary, you see the cable here and power supply by means of a cable. This is certainly also the status quo right now and what you can buy on the market. Coming back to the charging. So consider the workday, which is generally 8 hours in its length and is potentially segmented into two 4-hour parts. I mean, morning and afternoon with the lunch break, which would allow for charging time, for example. So here we did a quick calculation on comparing the diesel with the megawatt charging, which is kind of the gold standard right now and the state of the art that is in its research right now. So the C rate, meaning the capacity, the full capacity the vehicle can retain within 1 hour would be 1. And so for diesel, the gas inflow into the vehicle when tanking is about 21. So I could fill it up 21 times per hour, meaning I need 2 minutes to charge the combustion vehicle. If I look at the megawatt side, I can bring it down to 26 minutes. That's kind of as good as I can get right now in this example case, which would mean there may be a solution that even if we cannot power throughout the whole day, we may do so for 4 hours, then charge in the midday time, and then use the next 4 hours with the, again, charged vehicle. So yeah, this is what this example case should emphasize. And many applications may become feasible due to this technology. So very quick, looking at the services. That was a question that was asked of the organizers of the conference. So what are the services that companies can offer their customers right now? And I only want to emphasize one point here, and I think this is to include not just the product, but the service as such. Meaning, we just talked about this operational planning, right? When do you charge? How much do you charge? And having those calculations done within some companies is what we see right now. So they are not offering just their product, but they are very often the times offering a service additionally to the product itself, so that the operation of the product becomes more efficient, more effective. And there are companies like Volvo, MAN, or Daimler offering different services right now. Not to emphasize any one of those here, but just to give you an example of what is coming and emerging there on that end. And I think this will increase furthermore because we see such trends also in the automotive industry, where this integration along the value chain is happening. So let's get a little bit more technical. Considering NRMMs, when we are thinking on electrifying all those drivetrains that you see here on the right-hand side, versus what we already did, and here just an example of some electric vehicles. So what we see is we have a high volume and low diversity in the EV sector that has already built up knowledge, and now we're thinking on transferring this knowledge into the NRMM sector, which has a high diversity and low volume. So completely different requirements, and this is far more challenging, I think. And this is why, there's still some research needed. And one thing I want to emphasize here is with this little calculation, look at the topology of the drivetrains. So consider the agricultural sector, the construction sector, many different requirements that are there. And if I'm a company now, so this is the thought train here, that wants to build 10 machines. I have now catalogs of different suppliers, let's say 20 battery catalogs, 20 motors, and I can choose between 20 different inverters. And I consider, in my development phase, 5 topologies, meaning the arrangement of how I connect the motor with the auxiliary components, etc. So that would make up 400,000 variants. Of course, no one will manually go through every one of these and evaluate which one is the best. So what we are doing at RWTH right now is also considering different drivetrains. I give one example in the end. Doing topology research, to putting tools into place that allow for simplification of this rather complex matter. So this is one, knowing what to do. Then we need to choose from components, finding the right components right now. I think you all know that supply chain issues are there right now. I will emphasize those in a minute. And then you need to consider your application as well. And those all have to come together to build one homogeneous product or even service in the end. So this is on this end. I think I skipped those slides for now. If we want to get a little bit more technical, we can. But I would like to go a little bit more on this. So that was the status quo. It's a very diverse field where we have currently rather low volume production versus high volume and low diversity in the EV sector, relatively, right? Of course, there are different variants in the EV sector as well. And we are now trying to learn from that and to transfer the knowledge that we gain over the last years there to the NRMM sector. Before we go in there, and I will give you some examples here in the third part, let's look at the second part. And I structured this in 3 different phases: beginning, evolution, and revolution, and 2 special chapters on batteries, because I think their importance needs to be underlined here. So starting off, we see that we have a chart here: energy demand versus distance versus the weight and the size of the machine. And the further we get here on the x-axis and the further we get on the y-axis, meaning up here, the more difficult it becomes on electrifying those vehicles. Earlier on the economic chart, you could see that within this region here, there are already many electrifications happening of drivetrains, but especially for applications like tractors, combine harvesters, and heavy construction equipment that also has to work remotely, there are still very, very large challenges. And so therefore, we now have to consider and think, how far can we get here? Like how far can we move up this chart? So looking at what is happening right now. So the first one is electrifying everything that can be electrified right away. And this holds for, as I mentioned with the cable, for stationary energy or for rather stationary mobile equipment, and for small equipments that don't need such a high energy densities, like carrying equipment on machine shop floors or some maintenance machines. Those are rather suitable for electrification right away. So this is kind of the first phase, and we are talking about 2 tons to 5 tons in machine size roughly. So looking at a little bit further, what we also see that there are many prototypes built. So many companies in the last, let's say, 10 years came up with different designs, with different ideas on electrifying the equipment, and that was already given. We are talking about a tonnage here, a machine size of about 7 tons. As I said, these were prototypes. There were not really many serious production equipments yet. And then, if we look at it further, there are also, besides those purely electrified prototype concepts, hybrid concepts that are in development right now or have been established. So they're trying to get the best out of both worlds right now. And now I would like to see, together with you, can we bring this up to the next level, meaning fully electrifying this? Also, not just for the small applications, but for the bigger ones as well. And this is what we do on the next slides. Before we jump into that, we always have to consider that the one thing is the technological potential that is there, but the other question is, can that potential also be accessed right now? And there we look at the supply chain, right? So where do we see bottlenecks potentially? That is the one point on this. And where do requirements, due to also different potential that we have in the beginning, or considering IC, so combustion engines, we had like one central motor that was driving the whole machine usually. Now we have different topologies and we can optimize differently. So that means we could also reconsider the requirements on the drivetrain that may now change. And that would lead to more or less components that are actually needed in order to fulfill the same job, but using an electrified drivetrain. So, considering what we call now the second phase, and that is trying to not rethink everything. We'll come to that in the revolution part, but in order to optimize too, what I put on this last chart that you see, to push in this direction through engineering, through development, through research, etc. Increasing drivetrain efficiency and to increase the general limits that the battery technology generally holds right now. Just an example, a quick example on the battery efficiency would be, for example, and look at an excavator. It has usually a hydraulic pump in order to operate its auxiliary equipment. And what you can do there is, for example, operating through now electrohydraulics, operating these excavators at different hydraulic pressures, right? Not losing any excess hydraulic energy that has to be built. So meaning changing the pressure level as regulating the volume flow more efficiently. So this is one of the optimization strategies that we again and again see. Again, taking this excavator example, recuperation of energy, right? When you turn the machine, and it has to do with this movement very often in the day. Every movement can be or has to be braked, so you have to decelerate the tower again, and that can now be regained in energy that you have to put out for accelerating the tower, and that thereby we can also harness energy efficiencies. But again, coming back to batteries, we also need to push the limits further. And I would like now to look at the battery supply chain and the general battery technology before we come to the supply chain with you, to give you a little understanding of where we are in terms of battery. One or the other may already think like, okay, what about fuel cell? I will touch on that in the end a little bit, but I would like to emphasize or put the emphasis on the battery field in this presentation. So, a lot of engineering and development is happening right now. This is our pilot line at eLab, and you're invited to take a virtual tour afterwards when you receive the presentation. that would be a little bit beyond the scope of this presentation. I just wanted to mention it, so if you like to have an in-depth view on how the research is done, please have a look. To give you a little background on the batteries, functionality, we have basically 4 components. So one is the active material, we have the electrolyte, we have the electrode foil, where the active material is coated on, and then lastly we have the separator. And these are really the 4 key components which everyone has to deal with if he wants to build or she wants to build a high-performing battery cell. So there's research really going on in every field, I would say. This one is always very much discussed, so I will emphasize this in today's talk a little bit. So on the cathode side, so the positive side of the electrode, of the battery, so one of the electrodes, we have different materials that are available. If you look on the right-hand side, this is NCA, a material which Tesla formerly used a lot in their vehicles. I think it's not the most common used material anymore, but this is kind of where things started, and it has its usage. Considering other technologies such as NMC, and NMC is nickel manganese cobalt oxide, which comes in various forms and various weight percentages, meaning the mixing of the different material components. We see different performance aspects there. One always has to consider these points critically. If you look at those closely right now, they all change a little bit, and it also depends on the later cell design. Nevertheless, this technology here is, in terms of energy density, currently kind of the gold standard, I would say. Looking at on the right-hand side, this is an interesting material, which is lithium iron phosphate, which was believed to be dead about 4 years ago. Everyone was thinking, okay, this was an old technology, it doesn't have any use. And then suddenly, on the Asian market, there was some innovation happening, and now everyone is talking about LFP again. You see, it doesn't have a specific energy density, but it doesn't need cobalt, it doesn't need high nickel content, or nickel at all actually. So it's very environmentally friendly, and it's cheap. So, and it has many more benefits as well, I cannot go into right now. But just said that, this is emerging right now again. So even though many considered that it won't. On the anode side, we have a similar picture, choosing different technologies. I won't go on detail on that right now. So now you take the chemistry, you build it up into a cell. So round cell, prismatic cell, and pouch cell are different formats that are available. And then you have to consider, how do I take those cells, depending on the format that I use, into the vehicle. And just using the EV example here, there are different ways as well. You can build modules, but you can also do a whole pack integration, or even integrate into chassis. And I'm emphasizing this here because these are thoughts that have to be reminded when you design NRMM equipment as well. Because consider we have a high variance and we need a high modularity. So the research that has been conducted here may also be important for later as well. Then I would just quickly like to invite you to have a look at the battery atlas. You can, I think that there's something we can do afterwards. But there, within our network, together with the chair of PEM and Battery News, researched what are the different key players in the field currently. And this is what we come up with then, our different landscapes. And there you really can have an overview of who is actually doing what in the field right now, if you're looking for suppliers. As said, the link is in the presentation. I will just, in terms of the time, skip over those details, but also in the panel discussion, feel free to later on ask a question about it or connect with me in the break. So I think this one we will skip as well in terms of the timing, which just emphasizes the field of battery testing and focusing on the last part on the different phases. So in terms of revolution, what is happening now? The question is fuel cell the answer on revolutionizing the whole field. We saw that the evolution will heavily depend on batteries. And for the revolution part, maybe fuel cell will have its role. But to be honest, we don't know yet really what the potential will be. There are prototypes, as I highlighted earlier, that may actually result and find its way into serious application, but currently we cannot say for sure. So here are a couple of examples that try to bring the fuel cell technology forward. What is certain though, that the battery field will be present in the future, and it will find also new ways. So meaning it's not only the drivetrain that will change and electrify, but maybe due to the higher flexibility that emerges, we will see different applicational topologies. So for example, combining different smaller harvesters into one harvesting system, to put this as an example here. And some prototypes are in the field and being tested right now as well. So, quick emphasis on what is now in front of us looking into the future. I think it's important to emphasize that we have a market pull always, and when a product becomes economically viable, but we need to sustain this technology push phase. And I think for NRMMs, we are right in that phase right now. And there with eLab, for example, we would just like to support on doing research there and bringing certain technological innovations forward. We had gathered some experience in the heavy-duty industry that may be transferable to certain NRMM applications. And what I would like to emphasize in the final part is again this topology part. So as I said, the number of variances is very big, and we need to try to simplify, or at least to get an overview. So our researchers are also having a close look on the solutions that are available there. And yeah, we may also be able to support you on that end. And lastly, if in case you're further interested in eLab and what we do, just contact me. We have a network going on that is trying to really foster industry and research collaboration, and I can only say, yeah, just connect and let's see how we can bring NRMM development forward. So thank you for giving me the time to talk to you. I know it was a quick presentation with a lot of information. As said, we will digest it also in the panel discussions later on a little bit more. And in case of questions, just contact me anytime. Thank you very much.
Thank you.